Okay, hello everybody. Can someone please confirm they can hear me? Anybody? Yes, okay, thank you. So I need to make a few announcements. First is that there will be an additional extra credit assignment available. It's going to be optional, of course. It'll be based on mastering physics, available roughly for a week starting December 1st, which is a couple days after we all get back from the Thanksgiving break. It'll be graded like a normal homework and worth up to 0.5% of the final course grade. The hook is that credit will only be given to whoever does the assignment if the entire course reaches at least 75% participation level in the SRTEs. So I value your feedback, and this is a way that I can encourage you to provide that feedback. And I think the SRTEs will be available from November 30th to December 13th. I'll also mention that homework 7 is due Monday, December 7th, and homework 8, so this is the last week of classes, and homework 8, which is the shorter assignment, is due Friday, December 11th, the last day of class. There will be extra office hours for finals week. Those will be announced. And we have a third quiz coming up. And I just want to give you some information, though, first about the final exam. So that'll be about 18 questions, roughly a third of which will be new material that hasn't yet been covered in any quizzes, so post-quiz 3 material in particular, and 2/3 from previous material. And the exam itself will be split into 2 40-minute sections with roughly 10 or 15 minutes break in between. I will be posting some optional practice problems both for quiz 3 and for the final. And I will also be posting, or I should say Dr. Van Hook will be posting sample quiz 3 and sample final exam for you to use as practice. So what I'd like to start covering now is quantization of energy, by which we mean energy can only assume certain discrete values. And this, it turns out, as you'll see, is a consequence of 2 things. One, that matter has wave-like properties, which we showed previously. You remember we showed the pattern that occurs when we send electrons through a pair of slits, one at a time. They produced an interference pattern on a screen that was exactly like what you expect from waves, or from something that had wave-like properties. So we concluded that electrons, even though we like to treat them normally as particles, do have wave-like properties. So that's the first thing, that matter has wave-like properties. And the second thing is that they're confined, or I should say, if a particle with wave-like properties is confined, then it will exhibit interesting behavior. And in particular, its energies, the energies that it can have, will be fixed to certain values, quantized. And the reason for this happening is that if you want a particle that has wave-like properties, or indeed if you want a wave to remain alive, it can't destructively interfere with itself. In fact, it needs to constructively interfere with itself. And the way it does that is by forming a standing wave. So let's see what happens if we apply that requirement. And we're going to use a very simple model to start out with. And that's a particle that's confined to just a one-dimensional structure, which of course doesn't really exist in the real world. But that's what we're going to use as our simple model. And this is also known as a particle in a box, sort of more generally. In this particular particle in a box model, the box is one-dimensional, has length capital L. So what are the possible wavelengths that can produce standing waves? So think back to a closed pipe. So here's a pipe. It's closed at both ends. So the boundary condition for standing waves, sound waves in this case inside the pipe, is that we had a node at both ends. So there's one example of the wave that could fit in there. And I'm just drawing, a few time snapshots of that wave. We could also have, and let me just draw a little bigger here so I can make an easier to see diagram. We could also have for nodes at either end, you could have a wave that looked like this stuck inside. And, we could keep drawing things like this at higher and higher values of n, the integer n, to determine how many, or what wavelength could fit into this box of length L. And that was for sound. We could do the same thing for an electron inside, or a particle inside of a one-dimensional structure, using the de Broglie relationship between the particle's momentum and its wavelength to determine what its wavelength is, and then require that in order for that particle to remain inside of that box, it has to have a standing wave that is supported by that wavelength. So that's a lot of words. What we're just going to do is take the de Broglie wavelength, which now has a little subscript n to indicate that it's going to be able to assume only certain integer values, as we'll see in a second. So the wavelength is Planck's constant divided by the momentum of the particle. And the momentum of the particle is just mass times velocity. We're assuming that this is non-relativistic. And that's just equal to 2L over n, just like we wrote up here. And from that, you can then solve for the velocity, and you see that it has certain discrete values that it can assume. So if n equals 1, it's equal to h over 2lm. If n equals 2, it's equal to 2h over 2lm, and so on. And it can't be anywhere in between there. In this particular model, this particle cannot have an energy, a velocity that's equal to 1.5 h over 2lm. All right, so if we've written down what the velocity is, then we can easily write down what the energy is. Again, assuming this is non-relativistic, we can just write down that it's equal to 1/2 mv squared. And if you go through that relatively simple algebra, you see that the energy levels that are allowed are given by n squared times something in parentheses. That something in parentheses is the ground state energy of this particular system. And more importantly, what you see is that there's this relationship now between each of the energy levels. They depend on the value n squared, which is an integer. And so the energies can only assume certain discrete values. So they can assume the value E1, whatever that happens to be, depends on the mass of the particle and the length of the box, in this case, in this simple model. Or it can be 4 times that, or it can be n equals 3, 9 times that, and so on. Can't be anywhere in between. You can't have 8 times that. This particle cannot exist inside a box of length L with an energy where the energy is equal to 8E1. That's just not allowed. Now, when people first wrote this down, they got understandably kind of excited because one of the long-standing problems was to determine where this Balmer series equation came from. You remember that this Swiss school teacher came up with this description of the wavelengths that were emitted from hydrogen atoms. And he found that they obeyed this formula shown down there at the lower right. And there was, for 30 years, an effort to try to figure out where that formula came from. One of the things the formula has, one of its salient characteristics, is it has the square of an integer in the denominator there. And now we're seeing in this very simple model that the energy of a particle in a one-dimensional box depends on the square of an integer. And the reason that that's interesting and why those are related is, of course, the wavelength of light, lambda, is related to the energy of that light. And the energy of that light, or the photon, is related to the difference in the energy levels of hydrogen. So the fact that an n squared comes out here suggests that we're on the right path. Here's another thing that suggests we're on the right path. This is a more quantitative example of a particle in a one-dimensional box. So in this case, it's a proton, which has that mass. And we're going to assume that it's confined to a one-dimensional box and that it emits a gamma ray photon with an energy of 2 million electron volts when it makes a transition from an n equals 2 to an n equals 1 energy level in this box. So the question is, given that the energy emitted is 2 million electron volts, what's roughly the length of the box? So we can just use this expression down here to figure that out. So we're going to try to solve for the quantity L, basically. And in order to do that, we figure out what is the energy difference between n equals 2 and n equals 1 for a proton inside of a one-dimensional box. The energy at any individual level is just given by this. So the energy difference between two levels is just, in this case, n equals 2 and n equals 1 is just E sub 2 minus E sub 1. So that's going to be 4 times this quantity in parentheses minus 1 times the quantity in parentheses, or 3 times that quantity in parentheses. And that is the change in energy, and that must correspond to the energy of the emitted gamma ray of 2 million electron volts. So now we can just rearrange the terms in this expression and figure out what L is. And if you go through that, you find that you get 18 femtometers, which is roughly the scale, the size of an atomic nucleus. So why is that relevant? So the atomic nucleus is you can think of it as a box. It's not one-dimensional, obviously it's three-dimensional, but it's a box that contains, among other things, protons. So under those circumstances, you might expect that if somehow the nucleus of an atom were to get excited and one of the protons inside of it were to move from whatever ground state energy it has to the next energy level and then de-excite sometime later, that you would get energy that was emitted that was on the scale of 2 MeV, because we have a proton confined to a box that's roughly the size 18 femtometers. And indeed, that's the case. If you look, for example, at the decay of cobalt down to nickel, cobalt down to nickel, sorry, you can't see the nickel because of that pen icon down there, then the gamma rays that are emitted are roughly of the scale of, an MeV or so in energy. So these are nuclear radioactive decays. So the nucleus of cobalt relaxes, and in addition to other things, it emits high energy gamma rays whose energy level corresponds to what you might expect if you confine a particle with a mass of a proton to a box the size of a nucleus. So this is all very, very rough derivation, but it does show that we're kind of on the right path. All right, so coming out of the nucleus, let's get back to the atom as a whole. And we're going to try to apply these principles and concepts to the real world of atoms. And we're going to sort of follow the historical development, beginning with Niels Bohr, famous Danish physicist. He made the following assumptions. So first of all, he decided that he was going to assume that electrons can only be in certain orbits. They're not allowed to be any old place they like. Furthermore, he called the lowest energy level of an electron, say around the hydrogen nucleus, around the proton, the ground state, and the other states were called excited states. And whenever there's a change in state from ground to one of the excited states, or from an excited state to another state, then you get either photon emission or absorption happening. And finally, in order to explain how when particles, atoms, I should say, were accelerated, say, inside an evacuated tube, like the Crookes tube, if there was some gas inside there that you intentionally put in, and then you accelerated that gas, the collisions that occurred between that gas and other particles could result in exciting the electrons in those atoms to higher levels. And then when they relaxed back down to their ground states, light could be emitted. So it somehow was a way to explain how you could see these gases glowing with certain colors, certain wavelengths. So Bohr basically got rid of the problem of matter being unstable, because the electron going around the proton should be radiating energy, classically speaking, and therefore eventually it should just collapse into the nucleus. He got around that problem by just saying it doesn't happen. Matter is stable. Because electrons can only be in certain orbits, which is not a very compelling argument, obviously. But he said, okay, electrons can only be in certain orbits. And because of that, well, matter is therefore stable. And he also was able to explain with this set of assumptions the fact that spectra, the wavelengths of light emitted from atoms, were discrete and unique, and also that collisions could result in the emission of light. Okay, but getting into more detail, the model that Bohr came up with for the hydrogen atom was as follows. So first of all, they used hydrogen because it was the simplest atom element available, with just one electron and one proton. First, the assumption is that the electron, because it's so much lighter, roughly 2,000 times lighter than the proton, when the electron is orbiting around the proton doesn't move at all. You can make a similar assumption for the Earth going around the sun. So as the Earth goes around the sun, we can assume that the sun doesn't move at all by virtue of the Earth's motion. Of course, there is a small amount of tugging that the Earth does on the sun, and the sun does move a tiny amount as the Earth moves around it. So with an orbit like this electron around a proton, there are three things we need to consider. And we've already talked about two of these things. The first is what the total energy is of the orbit. The second is, because it's circular motion, we need to take into account what the force is and what's keeping it moving in a circular path, in other words. And the new thing that we're going to consider is, because we know now that this electron has wave-like properties, we're going to insist, it has a de Broglie wavelength, we're going to insist that that electron form a standing wave around the proton. So first of all, what are the components of the energy of the electron? So we've already written these down. There's the kinetic term, 1/2 mv squared. And then there's the electrostatic potential term, which is just, in this case, minus ke squared over r. And then the total energy, that's the electrostatic potential, right? Because you have an electron and a proton, two absolutely charged particles. So there's a potential energy term between them because of their charges. So the total energy is just given by this expression down here at the bottom, the sum of the kinetic and potential energies. So now what we're going to do is bring de Broglie in from Bohr's future. De Broglie came up with the de Broglie wavelength idea, I don't know, roughly 5 or 10 years after Bohr came up with his initial idea of the atom. So we're not exactly following the historical path, but we'll get to the same ultimate position anyway. So what we're going to do, using the idea of the de Broglie wavelength, as with the one-dimensional particle in a box, where we required that there's a standing wave between two endpoints, we're going to do the same thing, but instead for a circular path. So can anyone tell me what the equivalent condition is for a circular path? The condition of a standing wave. So it might help to look at, this picture over here and think about how you would draw such a thing. Right, so someone wrote down that 2 pi r, which is the circumference of that circular path, is equal to an integer number of wavelengths, n times lambda. So with that condition, we will get, for this electron going in a circular orbit around the proton, an integer number of wavelengths from its de Broglie wavelength. And that means that we'll have a standing wave, because everywhere the troughs and the peaks will line up with one another. Also, remember that for circular motion, we have the force, which is the Coulomb force, and we set that equal to the centripetal force, the centripetal acceleration times the mass, which is mv squared over r. And from that, we can get this expression for what the square of the velocity is for, a particle moving in a circular orbit, or in this case, an electron moving in a circular orbit around a proton that's held in place by the electrostatic force. All right, so we're going to now bring all these things together and see what comes out. So the de Broglie wavelength for lambda is the first thing we're going to put in. So that's what we did over here. So it's h over p, where p is just mass times velocity. So that's the condition, 2 pi r equals n h over mv. And then you can solve for the velocity in that equation. So the velocity is just n h bar over mr, where here I'm using a new definition, h bar, it's just h over 2 pi. It just saves a little bit of writing, that's all. We also wrote down on the previous slide an expression for v squared. So we said that that's equal to ke squared over mr, but we can also see from here that v squared is equal to all of this squared. So if we put those two things equal to one another, what do we get? So we're putting these two things equal to one another. We solve for r, and what we get is that r, with a subscript little n, is equal to n squared, which is an integer squared, times a bunch of constants. And those constants now have a special name in honor of Niels Bohr. It's called the Bohr radius. It's about 0.053 nanometers. And what this tells us is that the radii at which an electron can exist in this very simple model are quantized. In other words, they can only assume certain values of a sub b. So let's answer this question here, this poll. What does the r sub n equals n squared a sub b tell us? Okay, get your answers in, please. All right. So most people chose B. That's the correct answer. And what this tells us is that the electrons can only orbit at certain radii. Another way of saying that is that the radii are quantized. Given that, we can also take an expression for the total energy and see if the radii appear, or the radius appears in that expression. And from that, we can see what values of the energy are allowed for this electron. So we wrote down last time, and just recently, that the energy of the electron is equal to a kinetic energy term and a potential energy term. And you can rewrite the kinetic energy term in a form that allows you to put everything together and get just this really simple looking expression, which involves the radius, which we're now labeling again with the subscript n. So what this tells us is that if we plug in n squared a sub b for r sub n, is that the energy levels, which we should probably label E sub n, are equal to minus 13.6 divided by n squared in electron volts. So this means that the energy is quantized. The lowest energy, or I should say the highest magnitude energy, is 13.6. The lowest energy is minus 13.6 divided by n equals 1 squared. So that is the energy of minus 13.6 electron volts, is the energy of the electron in the ground state. That's how much energy it takes to liberate that electron and ionize hydrogen. If n equals 2, then the energy of the electron in that particular orbit is 1/4 that quantity, so 3 something electron volts. So given this expression for the energy, we can now find an expression for the wavelength of light in a transition from a state n to a state m. And the reason we want to do this is, again, we want to replicate or get the Balmer series to appear from what could be considered first principles. So the first principles are that we have an electron orbiting in a circle, we have electrostatic attraction, and we have a wavelength that describes this electron, the de Broglie wavelength, and we require that there's a standing wave. And with those conditions, we ended up with this expression. And now let's recast that into a form so that we can figure out what the wavelengths are when we move from one value of energy, n, to another value of energy, m, and light is emitted. So to do that, we use the relationships for light that says energy is Planck's constant times frequency. And of course, frequency times wavelength is equal to the speed of light, c. And if you do all that, what you find is that you get an expression that looks like this, where the lambda 0 is 91.12 nanometers. That looks exactly, in exactly the right form as the Balmer series. So this was a major advance, being able to finally derive from some relatively straightforward and easy to understand physical principles where this Balmer equation came from. Remember, Balmer was this Swiss school teacher who observed the different wavelengths of hydrogen and noted that they obeyed this mathematical relationship between one another. So the one small minor point that needed to be addressed was the fact that on the one hand, we had 91.18 in front, so that was the right value. But the derivation that we went through that has, this lambda 0 is 91.12. Can anyone think of what, approximation we made at the beginning that might explain this difference? You can put it in the chat. Right, so two people made some good observations. First of all, the movement of the nucleus. So that's the answer that has the biggest impact. So that's the approximation that has the biggest impact on this difference between 91.12 and 0.18. The fact that we assume that the proton didn't move, when in fact, what happens is the proton does move back and forth as the electron goes around it. If you take that into account, you get very close to the right value, 91.18. If you want to get even closer, you need to take into account relativistic effects. Okay, so this model basically works. It gives us not only the Balmer series, but it also tells us about other sets of transitions. So the Balmer series was convenient because it was visible. So it appeared in the visible realm. And it was for transitions from the n greater than or equal to 3 state down to the n equals 2 state. But you can have other transitions going on. For example, the Lyman transition was at shorter wavelengths, more energetic. This was not possible to see with the naked eye, so it took longer to discover these. And similarly, the transitions called the Passion series, where the light that was emitted was in the infrared and also not visible at lower energies. And this formula works for all of those. Okay, so there was a question in the chat, which I'm now going to be able to answer, about hydrogen-like ions. So if you have an ion with a single electron in it, you would kind of expect that it would behave roughly like the hydrogen atom with a single electron in it. So the two that are relatively easy to make and keep around long enough to make measurements on are singly ionized helium and doubly ionized lithium. So the helium consists of 2 protons and 2 neutrons in the nucleus surrounded by 2 electrons. If you remove one of those electrons, then you have a singly ionized helium, He+. So you have 1 electron with a nucleus that not only has, larger mass because it's got 4 particles in it, 2 protons, 2 neutrons, instead of hydrogen's 1 proton, but it also has twice as much charge. So that additional charge is going to have an effect. And in a similar sense, for doubly ionized lithium, which normally has 3 electrons going around it, now if you remove 2 of them, you have 1 electron that's going around a nucleus that consists of 3 protons and I think 3 neutrons. So it has that electron is just like with helium, He+, is going to feel more tightly bound, more attraction to the nucleus than in the case of hydrogen, because the amount of charge at the center is substantially larger. It's twice as large in the case of helium and 3 times as large in the case of lithium, doubly ionized lithium. All right, so take into account the fact that there are now, instead of just 1 proton in the center, Z protons, where Z could be equal to 1 if it's hydrogen. That changes the electromagnetic potential term. So the potential term is just related to the product of the charges, so the electron charge and whatever's in the nucleus, divided by the radius times some constant. So this means that the potential term that we used previously in the total energy of the electron now has this factor of Z in it. So if you go through the algebra, you'll see that the radius or the allowed radii change by this factor of 1 over Z. So they're going to be, the electrons are now going to be orbiting closer in to these higher charged nuclei, as you might expect. And you also, if you continue using the factor Z, you'll see that the energy levels end up having this Z squared in the numerator. So if you put in Z equals 1 for hydrogen with a single electron, so that's neutral hydrogen, you see that you get back what we wrote down before, so that's good. If you look at singly ionized helium, then that Z is going to be 2, So Z squared is 4. And you can see the energy levels are going to be 4 times as deep as they are for hydrogen. And for lithium, obviously then instead you put in Z equals 3. So then you'll get Z squared of 9. And so the energy levels will be even that much deeper. All right, so consider this question here that I'd like you to answer. So compared to hydrogen, ionized hydrogen-like atoms, like He plus or lithium plus plus, will be what? Easier or harder or equally hard to fully ionize? And what will the wavelength of the radiation be compared to hydrogen? Okay, get your answers in, please. Okay, so most people chose C. That's the correct answer. So we expect that because these electrons are going to be more tightly bound to the higher charge nucleus, and there aren't any other electrons around to get in the way, it's going to be harder to fully ionize a singly ionized helium to make He++, or doubly ionized lithium to make lithium++. It'll be harder to do that because that electron will be held in more tightly. And when that electron is excited into a higher level in that singly ionized helium or doubly ionized lithium, and it relaxes, it'll emit shorter wavelength radiation, more energetic radiation, because the energy levels are going to be farther apart. We can show that with something called an energy level diagram. So let me just explain what this is. It's probably fairly obvious to most of you. We're just basically making a plot of this equation up top here, putting in different values of n, and then drawing a horizontal line for each of those values. So for n equals 1, we have minus 13.6. For n equals 2, we have minus 3.4, and so on. The advantage to drawing diagrams like this is that you can see sort of right away what absorption lines and emission lines you might expect. So typically atoms are in the ground state. So the absorption lines are lines that you see when you shine light at all wavelengths onto a sample. And there are certain wavelengths that don't get through. And the ones that don't get through are the ones that get absorbed because they equal the energy that's required to move from, say, the ground state up to the n equals 4 state. So there's a particular wavelength of light that's just right to excite electrons from 1 to 4. And so those photons basically get removed from the light that you're putting in, and you see an absorption line. And you could also, of course, have the ground state up to n equals 2 and so on. Once you have an electron that's excited into a higher state, then you can get an emission line as it relaxes and moves down to a lower energy state. So an example is indicated by the 4 to 2 transition here, which results in the emission of light that has a wavelength corresponding to the energy difference between the n equals 4 and n equals 2 states. So let's make the same diagram, but for helium, singly ionized helium. So for singly ionized helium, it's a hydrogen-like atom, but it has Z equals 2. So that's shown right there. And when we square that, we get 4, obviously. And 4 times 13.6 is 54.4. So now the energy levels are much deeper. They're deeper by a factor of 4 compared to hydrogen. And that's illustrated by this energy level diagram. So here's the ground state. It's at minus 54 eV instead of the minus 13.6 eV for hydrogen. And the states are separated by larger amounts of energy. So the energy between here and here and here and here and here and here are larger than the corresponding separations for hydrogen. So it takes 54.4 electron volts to fully to liberate one electron, or this remaining electron, from singly ionized helium, which will make doubly ionized helium when you do it, whereas it only takes 13.6 eV to ionize neutral hydrogen. Just another way of saying that because the nucleus has a higher charge, in the case of singly ionized helium, it's holding that electron in more tightly, so it's harder to get that electron released. Okay, I'd like to consider this following question here, which says, at typical temperatures when these measurements are made, it's found that absorption wavelengths are a subset of the emission wavelengths. So there are more emission wavelengths than absorption wavelengths typically observed. So this figure here shows, one of each. So it shows an absorption and an emission wavelength. And the question is, why do we typically see more emission wavelengths than absorption wavelengths? So you can answer the poll now. Okay, get your answers in, please. All right. So there's a fairly wide range of answers. The correct answer is C, that atoms are typically in the ground state. So if you draw a little picture, you can see why that means that there will be more emission lines than absorption lines. And that's simply because you basically can only start, or typically only start, from one level whenever there's an absorption. Namely, you start from the n equals 1 level. So you can absorb from n equals 1 to 2 or 1 to 3, etc. But you rarely absorb from 2 to 3. So that doesn't usually happen. On the other hand, once you have an electron or an atom whose electron is excited up to, say, the n equals 3 level, then you can get not only a transition from n equals 3 to 2 and n equals 3 to 1, but you can also then get from n equals 2 to 1. So you can see just in this simple case, you can get three emission lines and only 2 absorption lines. In principle, there is this absorption line. It's just you just don't see it very often because most of the atoms are usually in the ground state when you start out. All right, so let me recap the discussion that we've just had about quantization. So we put together a few simple ideas. So the basic mechanics of centripetal acceleration from Newtonian mechanics, basic electricity and magnetism from physics 212, electrostatic attraction, and finally a new concept that particles like electrons can be described by a wavelength, a de Broglie wavelength. And putting those three things together, we have a pretty successful model of the hydrogen atom. The problem is that the model fails miserably if you have even just a slightly more complicated neutral helium atom, where neutral helium has 2 electrons in orbit around the helium nucleus. That additional electron basically makes it impossible to use the Bohr model and to get anything predicted from it. So by demanding that there were an integer number of wavelengths, de Broglie wavelengths in this circular path, we got quantization rules, and that's very important. But if we really want to understand what's going on properly and in 3 dimensions, we need to have a wave equation that describes it. So that's what we're going to work on next, and this will culminate in something called the Schrodinger wave equation that underpins all of quantum mechanics. And just to sort of lay the groundwork for that, it feels like if you're in mechanics and they write down F equals ma, that actually came from somewhere, and it's it's a law. But in fact, it was basically pulled out of thin air by Newton, and there's no underlying reason why F equals ma should work, but it does, and it makes a lot of predictions that like that planets will be in orbit around stars and things like that. And that apples will fall to the ground. So it works, and it makes a lot of predictions that also work, and so we believe it is correct. In a similar way, because F equals ma and the basic rules of mechanics did not work at the atomic scale, a new equation was essentially pulled out of thin air by someone named Schrodinger to describe what happens when you have particles that also have wave-like properties, and they're confined in small regions, etc. And so that is what we're going to talk about when we get to the Schrodinger equation. So in order to lead up to that, we need to talk sort of more generally and remind ourselves more generally about wave equations. So the wave equation classically, which works for electric fields or water waves or whatever, is given by this partial differential equation. And the solutions to this equation are the familiar traveling waves, which have the form that looks like this, cosine times some function that is the difference of position and time, with the standard definitions for all those quantities. What this describes, this y of x and t, is a wave that's distributed evenly along the x-axis. So it goes from plus minus infinity along the x-axis. But particles like electrons and protons and so on are localized. So if we're going to hope to have any success in describing particles as waves, we're going to need to figure out a way to localize those waves to describe the localized particles. There's a name for a localized group of waves. It's called a wave packet. And the first exposure to this that you might have had is when we talked about, or when you saw in a course, the concept of beats. So I'll remind you that you get this phenomena when you have 2 different sound sources, for example, that are at similar but not identical frequencies, and they're played at the same time. What you will hear is the average of the 2 frequencies, and that average frequency will be modulated. It'll increase and decrease in volume at a frequency that's equal to the difference between the 2 frequencies. So that's illustrated over here in this figure. So the fast wiggles are the average, and the envelope here is the modulation that's called the beats. So if you have 2 frequencies, 1,000 and 1,002 hertz, then the average frequency you hear is 1,000 hertz. That's these fast wiggles here. And the beat frequency is equal to the difference between those two, which would be 2 hertz. So this happens 2 times a second. Okay. One of these beats here can be considered a wave packet. So we just had 2 waves when we put them together, and we got the wave packet. It's important to note that since the beat frequency is delta f, and the period, delta t, is just the inverse of that, 1 over delta f, then the product of those 2 things, delta t and delta f, is equal to 1. And this is related to the uncertainty principle, as we'll see soon enough. But just before I let you go, let's just expand the discussion slightly from 2 waves adding together to, say, 7. And if you do that, so here are the 7 waves, a bunch of different frequencies added together, and we get a much tighter wave packet now, smaller and sharper. We still have delta f, delta t, and now greater than or equal to 1. That greater than or equal to 1 comes from Fourier analysis, so we're just going to assume it's correct here. And the question that we're going to answer next time is what does this tell us, this relationship tell us, about the possible time lengths of a wave packet? What does it tell us about the characteristics of this wave packet? Okay, so I'll end there. I wish everyone has a nice holiday, a safe holiday, and I'll see you in about 10 days. Take care.
Hi, sir.
Hello.
Can I ask a question?
Yes.
So in the in the beginning of the class, basically, we were talking about de Broglie wavelength inside a small one-dimensional box, right?
Right.
In that, as we can see that En equal to n square E1, basically,
Right.
and we solved it in terms of basically Bohr's model. We got 1 by n square. So just asking this, both are not connected, right?
I didn't follow the question. So we have an n squared here, and if
In the numerator.
right.
And so in the Bohr's model, we have the n square in the denominator.
Well, but that was for.
13.6.
Oh, I see what you mean. So yeah, this is. Let's go back to the Bohr model. So yeah, in the Bohr model, that n squared appears in the denominator.
So I got the technique how we got to this point in both the cases. Just wanted to know if both of them are connected or not.
I mean, they're connected in just in the sense that you're confining a particle to a small region. But in the first case, it was a one-dimensional box, completely artificial. In the second case with the Bohr hydrogen atom, we're confining it to a circular path. And there's some other conditions that are being applied, namely that if it's in a circular path, what's keeping it in that circular path. So there's a lot more going on in the Bohr hydrogen atom. I don't think it should be so surprising that this n squared appears somewhere else compared to the very simple model we did before. I think what really matters is that there's an integer appearing at all, and that in both cases it's squared. So there's a relationship between them, but it's not, exactly one-to-one, because in one case it's in the numerator, and the other case in the denominator.
Yes, thanks. Sir, and one more question. I asked you some days back about the proper time of Peggy and Ryan.
Oh, right. Yeah, I did come up with I think an explanation to that. I think the issue is that neither of them actually make a proper time measurement, because they don't have a clock that is at the same place as the two events that are occurring. So,
Sorry, sir. That means what? Like same
so
place as
if you think of the case where the person takes off in an airplane from Los Angeles and lands in New York, the takeoff occurs at a particular place. That's the first event, and it occurs, in the S prime reference frame. Let's just say it occurs at the origin in the S prime reference frame. And then when the plane lands in New York, the person is still in the same seat and has the stopwatch. We're still at the origin in the S prime reference frame. We make the second measurement, namely the time of the landing in New York. But if you think of Peggy and Ryan, the firecrackers for Ryan, for example, explode at two different positions in X. And the same is true for Peggy. The two events do not occur at the same place in her reference frame.
Okay, yeah. So basically, like both the events are not occurring at the same coordinates for their respective reference frames, and
Right,
that's why they are not proper time, right? So
correct.
in this case, who can take the proper time then?
Good question. I'm not sure anyone can, because these two events occur at different positions.
Okay.
I
Thank you, sir. Like,
think there might, no, I take that back. There might be a reference frame where you could measure that. I'll have to think about that. That's another good question. I don't know the answer off the top of my head. I don't think there is, but let me think more about it.
thanks, sir.
Sure.
So I will send you the email by tomorrow, I guess.
Okay.
Thank you,
Okay.
sir.
Yep. You're welcome. Bye-bye.
Yep. Bye, sir.
Professor,
Yes.
I had a question. So now after Thanksgiving break, a lot of us students were going back home with different time zones.
Right.
Is participation still going to be graded during the time that class is scheduled?
So that's a valid question. The person who was just talking is in India right now, so he's got like 11 or 12 hours time zone difference. So it is possible to do, but I understand that some people might be in time zones where 8 in the morning East Coast time is really, really difficult.
Yeah.
So that's an interesting point that I hadn't really thought about. Let me confer with Dr. Van Hook and see what we can do.
Okay. All right. I appreciate it.
Yep.
Thank you.
Okay, if there are no other questions, I'm going to say goodbye. All right. Take care, everybody. See you next time.